Here, we now wrap up partial derivatives by discussing a few partial derivative applications, and that includes gradients, divergence, and curl. While there are more specific examples, all of them fall into the general category of these three. For example, if we talk about Maxwell's equations, it follows divergence and curl. If we talk about gradients, we can talk about the relationship between the electrostatic field and its potential and electric potential. Or in general, if we're talking about more mechanical systems like fluid dynamics, it all follows these three important applications, and all of these rely on an understanding in partial derivatives. So first, I want to talk about one specific example. Previously, we used integration, we used Maxwell's equations. Recall that the four Maxwell equations are given by the following. We will omit the details as necessary for simple discussion. So these are the four Maxwell equations, which unite all of electromagnetics. And we have also shown that, or we have also seen, or we've also discussed about how these equations led to the phenomenon that light was nothing more than an electromagnetic wave. Here, I want to, without showing all the details, I want to show that all these could be converted to the following equations. So in this specific situation, whenever we have a nabla operator and we take the dot product of this, both of which will be discussed in their own separate videos, this is the same as taking the partial derivative of each part, and let's suppose that it's given by three variables. Apologies. Whenever we take the gradient, or the gradient dotted with a vector, and we have the scalar product of the three added together. Apologies. We have del E del X plus del E del Y plus del E del Z, assuming Cartesian. Notice that for divergence, it relies on knowing that these are partial derivatives. Similar for curl, it also leads to a it also leads to showing partial derivatives. But even inside Maxwell's equations, we can see that for these two, we've discussed that the closed loop integral of the electrostatic field or the magnetic field is produced by changing magnetic flux or changing electric flux. Here, this explicit relationship is more clear when we can see that the changing magnetic field produces an electric field. Similarly, a changing electric field produces a changing magnetic field. And this relationship is what leads to the discovery that light is an EM wave. So through partial derivatives, through simple integration, we managed to show that all of it led to important fundamental applications within electrical engineering, but also wherever there is partial derivatives, we are talking about multiple parameters that we can adjust and we can utilize to try and understand a system more fundamentally. And one specific system would be in the realm of EM, or electromagnetic fields. I hope this gives you a good feel for partial derivatives and why they're so important. Next, we will discuss about multivariable integration and how we can complete the other piece to try and understand the notation for the different integration. Thank you.